Hi there. In this video clip, we will discuss how to select relevant features for classification using techniques like entropy, mutual information, and information gain. So basically, entropy is a measure of uncertainty, and when so uncertainty, you see, it increases when something is unpredictable. So let's say you have two teams playing and both of them are equally good. So both of them are competent, both of them are equally competent. So, the result is uncertain. Whereas if you have a team that's very good and a team that's not so good, then you can say that the uncertainty is less. Which means that when the probabilities are skewed, the probabilities of winning of one team versus the other, they are skewed, then we can say that the uncertainty is high. And when the probabilities are roughly equal, then we can say that the uncertainty is, sorry, it's the reverse, right? So when the probabilities are skewed, then we can say that the uncertainty is low. And when the probabilities are roughly equal, then we can say that the uncertainty is high. And a good way to give this relation to express the fact that skewed probabilities lead to a high uncertainty is by using this formula for entropy, and it says that it's minus p log p to the base 2 minus 1 minus p log 1 minus p to the base 2, where p represents the probability of one outcome and 1 minus p is the probability of the other outcome. So let's take a just just let's go into the details a bit. So you see that when you have p equal to half, and this is what happens, and you get log 2 to the base 2, and that is 1, and the unit used to express the entropy is bits, right? So if you have a logarithm 2, then your answer is expressed in bits, and if you have logarithm, natural logarithm, then the unit is nats. Okay, nats, right? That's nats. Okay, and let's take the case when the probabilities are skewed. One is probability 1 and the other one is 0. In that case, 1 log 1 will give you a 0 because logarithm 1 is a 0, and 1 minus p would become 1. I would, yeah, 1 minus p would become 0 because p is 1, and here you have 0 logarithm 0. Now this turns out to be an indeterminate form because 0 logarithm 0, because logarithm 0 is minus infinity. So this is an indeterminate form, but we note that this h of x in general is a continuous function in the interval from 0 to 1, and for values close to p equal to 0 or p equal to 1, the value of h of x turns out to be close to 0 or 1. I'm sorry, it turns out to be close to 0. For values of p close to 0 or 1, h of x turns out to be close to 0. So even though this is an indeterminate form, it's assumed that h of x is 0 when p equals to 1 or 0. Okay, so, and this is the case for binary case, right? Two possibilities when you have one or the other. Similarly, you could extend the same to many possibilities. So you could have many possibilities for a random variable, and that can be expressed by saying minus summation of over I pi log pi. Okay, and when you do that, so when you do that, yes, so you could get a maximum value. In this case the maximum value is logarithm 2 of to the base 2, which is 1, and in this case the maximum value you could get is log k. Okay, and it happens for a value probability equal to 1k, pi equal to 1k for all k, right? For pi equal to 1 by k for all I, then you get the value log k to the base 2. And in the case when the probabilities are skewed, only one of the values takes a value of 1 and all the others take a 0, then h of x takes a value 0, right? So the difference between the binary case and the multiple possibilities case is that binary case, for a probability of 1 by 2, meaning uniform probability, it gives the maximum entropy of 1. And for the multiple outcomes case, for a uniform probability of 1 by k, you get a maximum entropy of logarithm k to the base 2, which means there is more uncertainty when there are more possibilities, right? And that is true. When you then more there are more possibilities, there is definitely more uncertainty. So what you need to take also from this is that when you have skewed distributions, it results in low entropy, and when you have uniform distributions, it results in high entropy. So next we need to consider what causes the entropy to decrease, right? Or could there be a variable or a random variable whose knowledge could result in a decrease in the entropy? And that's what we want to answer. Now take this uh, you know uh, toy example. Supposing you have a team which has won 7 matches and lost 7 matches, and you have a star player who has played in 7 matches and who has not played in 7 matches. And when the star player plays, uh, you know, he wins 6 of the matches and he loses 1 match. And when he has not played, then you know the team has won only 1 match and lost 6 matches, right? So obviously this means that you can predict the outcome of the match by just asking whether the star player has played or not, right? So we want to devise a formula, by which would reduce the entropy when the knowledge with the knowledge of some random variable, with the knowledge of some value, right? Let's see how that can be done. So let's calculate the entropy in this case, right? When the star player has played and you have somewhat skewed distribution of 6 comma and 6 and 1, right? So the entropy in this case would be minus 6 by 7 log 6 by 7 to the base 2 minus 1 by 7 log 1 by 7 to the base 2, and that turns out to be 0.59, and we represent it as h of x under y equals to 0. Now what are x and y? Let's say that x is the outcome of the match and y is the knowledge of the random variable representing whether the star player has played or not, right? So in this case, this is the entropy of x, outcome of the match, given that the star player has not played, right? And so we can write the same thing for the case when the star player has played. So it would be minus 1 by 7 log 1 by 7 minus 1 by 6 by 7 log 6 by 7. You know, it turns out to be the same value because, in one case there is a 6 and in one case there is a 1. In the other case there is a 1 and the other case there is a 6, right? So what is p in one case is 1 minus p in the other case, and what is 1 minus p in one case is p in the other case, right? So it turns out that the values are the same. And this is h of x under y equals to 1. And now we want to somehow combine both these values to just reflect, one. We just want a single formula to reflect, both these, right? So we can say that we'll take an average, right? So we can average it out based on the occurrence probability of y equal to 1 and the probability of y equal to 0, right? And so when we do that, we get half into 0.59 plus half into 0.59, result is 0.59. Okay, so this figure here is actually called the conditional entropy. So if you want the formula for h of x under y equals to I, then that's simply the probabilities p log p, but the probability that you would take is conditional, okay, under the condition that y equals to I and summing over all j, right? And then if you want to find out the overall h of x under y, the conditional probability, and that's just the average value of all h of x under y equal to I. So obviously you would need to multiply by probability of y equal to I. So it's the expected value of all h of x under y equals to I. Okay. And another thing to note from here, that even though these probabilities are kind of skewed 6 by 7, 1 by 7, and when it is 0.5, 0.5, you get a entropy of 1. Okay, let's look at this figure here, right? So when you have p equal to 0.5, you get h equals to 1, and we can write h as a function of p for the binary case, right? Because it's just p log p minus of p log p minus p 1 minus p log 1 minus p, right? So h is just you can, in the binary case, is just a function of p. Okay, so when p equals to 0.5, you see that it takes a value 1, but when it's skewed 6 by 7, 1 by 7, the entropy reduces from 1 to 0.59, which means somewhere here, right? So yeah, so when p is around 0.85, you get a value of 0.59, and there's a steep decline. You see, from p equal to 0.85 to p equals to 1. So this is your, let's say, 0.85, right? So from p equals to 0.85, and you just extend this, right? So from a value of h of p equal to 0.59 for 0.85, there's a steep decline to h of p equal to 0 when p equals to 1, or when p equal to 0 as well, right? So that's the reason for, that's an explanation for this kind of a value 0.59, right? So there's actually a decrease of entropy from 1 to 0.59, but that actually means that there's a bigger change in the probability, right? So yeah. And now we need to know what is the mutual information and the mutual information of two random variables is just the difference between the entropy of the first random variable minus the conditional entropy of the first random variable under the condition that second random variable's value is known. Okay, and so it just means that the mutual information is the decrease in entropy observed when a particular random variable's value is known. Okay, which means that for if the variables are highly correlated, then you would expect that I of xy is larger. It's a value that's you know has a high magnitude. We will shortly discuss what values I can take, but I is larger when the features are correlated. That's what you have to bear in mind. And a little bit more on the properties of I, the mutual information. So it turns out that I of xy is symmetric, right? So I of xy is the same as I of yx, right? And you would note that I of yx is equal to h of y minus h of y under x, right? But these values are all the same. So it's a symmetric value, right? Also, note that h of xy is less than or equal to h of x. How do we know this? Basically, h of x is the uncertainty in the random variable x, and h of x under y is the uncertainty of x when a value y is known. So this always has to be less than h of x, right? Because if you know some random variable's value, it would definitely result in a decrease in the entropy of x, right? In the worst case, they are not related at all, which means that h of x under y would be the same as h of x, but it would never be greater than h of x. Okay, and that's so simplifying, we get h of x minus h of xy greater than or equal to 0, which means that I of xy greater than or equal to 0. So this means that the mutual information is a positive quantity. Okay, and also by definition I of xy is h of x minus h of xy, and because h of xy is a positive quantity, you can say that the mutual information is less than or equal to the entropy h of x. Okay, so similarly you can say by making use of the symmetric relationship that I of xy is lesser than or equal to h of y. So which means that the mutual information is bounded by 0 and the minimum value of h of x and h of y. Okay, so what is the use of all this, of the mutual information? That you can use a random variable to represent the category of examples. Instead of x, you have a variable c representing the category of the examples, and instead of y, you have a random variable representing the value of some feature, right? So then you could find out features which are relevant by just finding out features which give you a higher value of mutual information. And then about information gain, information gain is just a measure of how much the knowledge of a feature f decreases the entropy of a training set x, right? So given a training set, how much the knowledge of a feature f decreases the entropy with respect to the category, the entropy of a training set with respect to the category of the examples. You know, different examples would be labeled as coming under different categories, right? So it, so this means that the information gain is the same as the mutual information between the category and the feature, right? So with respect to, actually there are many different ways of looking at information gain, and some people like to use information gain, uh, you know, as an all, when they say information gain, it means Kullback-Leibler divergence, right? Which is another metric, right? But here in the case of especially decision trees, the information gain is actually the same as the mutual information. Okay. So the mutual information is a good quantity to use if you want to find out relevant features.